Imagine a star being torn apart by a black hole's gravity, its light stretched into a fiery halo as it spirals inward, a cosmic feast captured in stunning detail by the James Webb Space Telescope. This isn't just another image of a black hole, it's a revelation. For decades, scientists have puzzled over how these monstrous objects sustain themselves, growing larger by swallowing nearby stars and gas. But Webb's infrared vision has pierced the dust shrouds of distant galaxies, revealing a previously hidden process. Black holes aren't just passive vacuum cleaners, they actively sculpt their surroundings, funneling material into a spinning disk that radiates heat and light. The data suggests these hungry giants regulate their own growth, balancing consumption with outbursts that shape entire galaxies. This discovery doesn't just answer a fundamental question about black holes, it reshapes our understanding of how the universe evolves. What we're seeing isn't just a black hole feeding, it's the universe itself, devouring and rebirth, in real time. James Webb Space Telescope discovers how black holes feed themselves. This part of our deep dive into James Webb Space Telescope discovers how black holes feed themselves focuses on, explain plainly what was actually discovered/announced. Lead with the single most important fact, then fill in the necessary detail a curious newcomer needs to understand it. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have gazed into the cosmos, searching for answers to one of the universe's most enigmatic questions: how do black holes sustain themselves? These cosmic giants, with their immense gravitational pull, devour nearby matter, stars, gas, and even entire galaxies, but the process has always been shrouded in mystery. Until recently, the tools available to study these phenomena were limited, unable to peer deep enough into the dusty veils of distant galaxies or capture the faint signals of accretion disks around black holes. That changed with the launch of the James Webb Space Telescope, a revolutionary instrument designed to see further, deeper, and with greater clarity than ever before. Now, scientists have made a groundbreaking discovery. They've finally observed how black holes feed themselves, revealing a process that has shaped the evolution of galaxies across the universe. But how did they do it? Let's step through the journey of this discovery, from the telescope's design to the breakthroughs in observation and analysis that unlocked this cosmic secret. The James Webb Space Telescope, launched in December 2021, is a marvel of engineering and science. Its primary mission was to study the early universe, observing the first galaxies that formed after the Big Bang. But its capabilities extend far beyond that. With its advanced infrared instruments, JWST can peer through cosmic dust, which has long obscured our view of distant celestial objects. This is crucial because many of the black holes that feed themselves are located in the centers of massive, dusty galaxies, where their activity is hidden from optical telescopes. The telescope's two main instruments, the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, are equipped to detect the faint, infrared light emitted by these accretion disks, the swirling, superheated gas that surrounds a black hole as it consumes matter. These instruments, combined with JWST's unprecedented sensitivity and resolution, allowed scientists to capture detailed images and spectra of these regions, providing the first clear glimpse into the feeding mechanisms of black holes. But the journey to this discovery wasn't just about the telescope's capabilities. It required a deep understanding of how black holes interact with their surroundings. For years, astronomers have theorized that supermassive black holes, which reside at the centers of most galaxies, grow by accreting gas and dust. However, the exact process has remained elusive. One major challenge is that the material around a black hole is heated to extreme temperatures, emitting light across the electromagnetic spectrum. But much of this light is absorbed or scattered by interstellar dust, making it difficult to observe in visible wavelengths. Infrared light, on the other hand, penetrates these dust clouds more effectively, allowing scientists to study the accretion disks in greater detail. JWST's infrared instruments were specifically designed to overcome this limitation, enabling researchers to observe these regions with unprecedented clarity. The process of discovering how black holes feed themselves began with targeted observations of distant galaxies where black holes are known to be active. These galaxies, often referred to as active galactic nuclei, AGN, emit vast amounts of energy as their central black holes consume surrounding material. However, until JWST's arrival, these AGN were often obscured by the dense clouds of dust and gas that surround them. By using JWST's infrared capabilities, scientists could now see through these veils, revealing the structure and dynamics of the accretion disks. The telescope's high-resolution imaging allowed researchers to map the distribution of gas and dust around these black holes, while its spectroscopic instruments provided detailed information about the temperature, velocity, and composition of the material. This data was critical in understanding how the black holes interact with their environment and how they sustain their growth. One of the key breakthroughs came from the ability to measure the motion of gas around black holes. By analyzing the light emitted from the accretion disks, scientists could determine how fast the gas is moving and how it is distributed. This motion is directly related to the black hole's mass and the strength of its gravitational pull. For example, gas that is closer to the black hole moves at higher velocities, while gas farther out moves more slowly. These observations allowed researchers to estimate the mass of the black hole and track how it accumulates over time. Additionally, the spectral data revealed the presence of specific elements and their ionization states, providing insights into the physical conditions of the accretion disk. These findings confirmed that black holes are not passive consumers but active participants in their environment, regulating the flow of matter and influencing the surrounding galaxy's evolution. The discovery also relied on the collaboration between JWST and other telescopes. While JWST's infrared observations provided critical data, they were often complemented by observations from other instruments, such as the Hubble Space Telescope and ground-based observatories like ALMA, Atacama Large Millimeter Array. These telescopes operate at different wavelengths, offering a more complete picture of the black hole's environment. For instance, radio telescopes like ALMA can detect the cold, dusty material that surrounds the accretion disk, while X-ray telescopes can observe the high-energy emissions from the innermost regions of the disk. By combining data from these multiple sources, scientists could build a more comprehensive model of how black holes feed themselves. This multi-wavelength approach was essential in confirming the findings and ensuring that the observations were consistent across different methods of study. Another critical aspect of the discovery was the timeline of observations. The James Webb Space Telescope began its science operations in late 2022, and its first major observations of distant AGN were conducted in the following months. The process of gathering data was meticulous, requiring careful calibration of the telescope's instruments to ensure accuracy. Scientists had to account for various factors, such as the movement of the Earth, the thermal environment of space, and the subtle effects of cosmic dust on the light captured by the telescope. Over time, as more data was collected, patterns began to emerge, revealing the intricate dance between the black hole and its accretion disk. These observations were not just about capturing images, they involved analyzing vast amounts of data to extract meaningful insights, often requiring complex computational models and simulations to interpret the results. The significance of this discovery extends beyond understanding black holes themselves. By observing how these cosmic entities feed, scientists have gained new insights into the life cycles of galaxies. Black holes are not just isolated phenomena, they are deeply intertwined with the evolution of their host galaxies. As they consume matter, they release enormous amounts of energy, which can influence the formation of stars and the distribution of gas within the galaxy. This process, known as feedback, plays a crucial role in shaping the structure and dynamics of galaxies. The findings from JWST's observations have provided direct evidence of this feedback mechanism, showing how black holes regulate their environments and sustain their growth over billions of years. This has profound implications for our understanding of galaxy formation and the role of supermassive black holes in the universe's history. However, the journey to this discovery was not without challenges. One of the primary obstacles was the sheer distance of the observed galaxies. Many of the AGN studied by JWST are billions of light-years away, meaning the light we see today was emitted when the universe was only a fraction of its current age. This makes the observations incredibly difficult, as even the most advanced telescopes struggle to capture the faint signals from such distant objects. Additionally, the data collected by JWST is vast and complex, requiring sophisticated analysis techniques to extract meaningful information. Scientists had to develop new algorithms and models to interpret the data, ensuring that the findings were accurate and reliable. These challenges highlight the immense effort and collaboration required to make such a discovery, underscoring the importance of technological advancements in space science. In the end, the discovery of how black holes feed themselves is a testament to the power of modern astronomy and the ingenuity of scientists. The James Webb Space Telescope, with its advanced instruments and unparalleled sensitivity, has opened a new window into the universe, allowing us to observe phenomena that were previously hidden from view. By combining cutting-edge technology with decades of theoretical knowledge, researchers have finally unraveled a fundamental aspect of black hole behavior, shedding light on one of the most mysterious processes in the cosmos. This discovery not only advances our understanding of black holes but also deepens our appreciation for the dynamic and interconnected nature of the universe. As we continue to explore the cosmos, the lessons learned from JWST's observations will undoubtedly guide future research, inspiring new questions and discoveries that will shape our understanding of the universe for generations to come. The question of how black holes feed themselves has long been one of the most perplexing mysteries in astrophysics. Black holes, those enigmatic cosmic entities with gravity so intense that not even light can escape their pull, are not passive observers of the universe. Instead, they actively consume surrounding matter, stars, gas, and dust, through a process known as accretion. But how exactly does this process work? And why does it matter? The James Webb Space Telescope, with its unprecedented ability to peer into the infrared spectrum, has begun to unravel these mysteries, offering a deeper understanding of the physics that governs these cosmic giants. At the heart of a black hole's feeding mechanism lies the accretion disk, a swirling, luminous halo of gas and dust that orbits the event horizon, the point of no return. As this material spirals inward, it accelerates, heating up to temperatures so extreme that it emits vast amounts of energy, primarily in the form of X-rays and ultraviolet light. However, this radiation is often obscured by the thick clouds of interstellar dust that surround many black holes, making it difficult for traditional telescopes to observe the process in detail. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can penetrate these dusty veils, revealing the hidden dynamics of black hole accretion. The significance of this discovery lies in the fundamental role black holes play in shaping the universe. Supermassive black holes, which reside at the centers of most galaxies, are thought to influence the formation and evolution of their host galaxies. By consuming surrounding material, they release enormous amounts of energy, which can regulate star formation, heat interstellar gas, and even trigger the birth of new stars. Understanding how black holes feed themselves is therefore crucial to comprehending the large-scale structure of the cosmos. Yet, until recently, many aspects of this process remain shrouded in uncertainty. One of the key breakthroughs enabled by the James Webb Space Telescope is the ability to observe the interaction between black holes and their surrounding environments in unprecedented detail. By studying the infrared signatures of accretion disks, scientists have gained new insights into the physical conditions of the material as it falls into the black hole. For instance, the telescope has allowed researchers to measure the temperature, density, and velocity of the gas in these disks, revealing how the material behaves under extreme gravitational forces. These observations have also provided critical clues about the role of magnetic fields in the accretion process, which are thought to play a vital role in channeling matter toward the black hole's event horizon. But the implications of these findings go beyond the immediate mechanics of black hole feeding. The James Webb Space Telescope's observations have also shed light on the broader question of how black holes grow over time. Supermassive black holes, which can weigh millions or even billions of times the mass of the Sun, are believed to have formed in the early universe, but the exact mechanisms of their growth remain unclear. By studying the accretion processes of younger, less massive black holes, scientists can piece together the evolutionary pathways that lead to these cosmic behemoths. This, in turn, helps address one of the most profound questions in astrophysics: how did the universe evolve from its earliest moments to the vast, complex structures we observe today? Another fascinating aspect of black hole feeding is the phenomenon of relativistic jets, high-energy streams of particles that are ejected perpendicular to the accretion disk at speeds approaching the speed of light. These jets, which can extend for thousands of light-years, are thought to be powered by the immense gravitational energy released as matter falls into the black hole. While previous telescopes have captured glimpses of these jets, the James Webb Space Telescope has provided a more detailed view of their composition and behavior. By analyzing the infrared light emitted by these jets, scientists have been able to determine the presence of heavy elements and the conditions under which these particles are accelerated. This information is crucial for understanding how black holes not only consume matter but also influence their surroundings through powerful outflows. The James Webb Space Telescope's ability to observe these processes in the infrared spectrum is particularly transformative because it allows scientists to study black holes in environments where dust and gas are abundant. In many galaxies, the dense interstellar medium obscures visible light, making it difficult to study the accretion process directly. However, infrared light, which has longer wavelengths, can pass through these obscuring materials, revealing the hidden dynamics of black hole feeding. This capability has enabled researchers to observe black holes in a wide range of environments, from the dense cores of active galactic nuclei to the more isolated regions of the universe. By comparing these observations, scientists can identify patterns and variations in how black holes accrete matter, which in turn provides insights into the diversity of black hole behavior across different cosmic settings. Moreover, the data collected by the James Webb Space Telescope has also challenged some long-held assumptions about black hole accretion. For example, previous models suggested that the accretion process might be highly efficient, with most of the energy from falling matter being converted into radiation. However, the telescope's observations have revealed that this process is more complex than previously thought, with significant variations in efficiency depending on factors such as the black hole's spin, the properties of the surrounding material, and the presence of magnetic fields. These findings suggest that the relationship between black holes and their environments is far more dynamic and intricate than previously believed, with implications for our understanding of energy transfer in the universe. Beyond the immediate scientific implications, the study of black hole feeding has profound philosophical and existential significance. Black holes are among the most extreme objects in the universe, and their behavior challenges our understanding of gravity, spacetime, and the fundamental laws of physics. By observing how these cosmic entities consume and release energy, we gain a deeper appreciation of the universe's capacity for both destruction and creation. The James Webb Space Telescope's discoveries not only advance our knowledge of black holes but also remind us of the vast, mysterious forces that shape the cosmos. As we continue to explore these phenomena, we are uncovering the intricate web of interactions that govern the universe's evolution, from the smallest particles to the largest structures. In conclusion, the James Webb Space Telescope has revolutionized our understanding of how black holes feed themselves, revealing the complex interplay between gravity, magnetic fields, and the surrounding interstellar medium. These insights are not only critical for unraveling the mysteries of black hole physics but also for understanding the broader role these objects play in shaping the universe. By peering through the veil of dust and gas, the telescope has opened a new window into the cosmos, allowing us to witness the dynamic processes that drive the evolution of galaxies and the fabric of spacetime itself. As we continue to analyze the data from this groundbreaking mission, we are reminded of the endless possibilities that lie ahead in the quest to understand the universe's most enigmatic phenomena. For decades, black holes have captivated scientists and the public alike, not just for their mind-bending physics but for their role as cosmic engines. These invisible giants, with gravity so strong not even light can escape, have long been a mystery. Yet, our understanding of them has evolved dramatically over the past century, shaped by groundbreaking discoveries and technological leaps. The James Webb Space Telescope's recent findings about how black holes feed themselves are the latest chapter in this story, a story that began with Einstein's equations and has since unfolded through decades of observation, theory, and innovation. To grasp the significance of this discovery, we must first travel through time, tracing how humanity's view of black holes has shifted from theoretical curiosities to powerful cosmic forces. The journey began in the early 20th century, when Albert Einstein's theory of general relativity predicted the existence of black holes. In 1915, Einstein's equations described gravity as the curvature of spacetime, and in 1916, Karl Schwarzschild found a solution that hinted at regions where gravity would be so intense that not even light could escape. However, these ideas were largely theoretical, and the scientific community remained skeptical. It wasn't until the 1960s that black holes began to take on a more tangible form. Astronomers like Subramanian Chandrasekhar and John Wheeler helped solidify the concept, while observations of X-ray binaries systems where a normal star orbits a compact object provided early evidence of stellar mass black holes. These systems emit intense radiation as matter spirals into the black hole, a process that would later become central to understanding how these objects feed. But the true revolution came in the 1970s and 1980s, when astronomers realized that supermassive black holes, millions or billions of times the mass of the Sun, reside at the centers of galaxies. This revelation was driven by observations of quasars, incredibly luminous objects powered by gas falling into these massive black holes. The energy output of quasars suggested that something far more powerful than a single star was at work. By the 1990s, the Webb Space Telescope played a pivotal role in confirming this idea. Its ability to peer into distant galaxies allowed scientists to map the distribution of supermassive black holes and study their environments in unprecedented detail. These observations hinted at a connection between black holes and the evolution of their host galaxies, a link that would become a cornerstone of modern astrophysics. Yet, even as our understanding of black holes grew, many questions remained. How exactly do they accrete matter? What role do their surroundings play in their growth? The answers required more than just telescopes. They demanded new tools capable of capturing the faintest signals from the farthest reaches of the universe. Enter the X-ray observatories of the 2000s. Instruments like the Chandra X-ray Observatory and XMM Newton provided critical insights into the dynamics of black hole accretion. These telescopes revealed the presence of accretion disks, swirling disks of gas and dust that heat up to extreme temperatures as they spiral into the black hole. The X-rays emitted by these disks offered a window into the extreme physics at play, allowing scientists to measure the spin of black holes and study the behavior of matter under conditions that can't be replicated on Earth. However, while these observations were groundbreaking, they couldn't fully explain the complex interplay between black holes and their environments. The 2010s marked another turning point with the advent of multi-wavelength astronomy. By combining data from telescopes that detect visible light, infrared, X-rays, and radio waves, scientists could piece together a more complete picture of black hole activity. This approach revealed that black holes are not isolated entities but are deeply intertwined with their host galaxies. For example, observations showed that the growth of supermassive black holes often correlates with the formation of galaxies, suggesting a symbiotic relationship. The discovery of relativistic jets, high-energy streams of particles ejected from black holes, further complicated the picture. These jets, which can span thousands of light-years, hinted at the immense power of black holes and their ability to influence their surroundings on a cosmic scale. Yet, despite these advances, the exact mechanisms by which black holes feed themselves remained elusive, prompting the need for even more sensitive instruments. Enter the James Webb Space Telescope, launched in 2021. With its advanced infrared capabilities, Webb has opened a new era of black hole research. Unlike earlier telescopes, which struggled to peer through the dust shrouding distant galaxies, Webb's instruments can detect the faintest signals from the earliest epochs of the universe. This has allowed scientists to study black holes in their cosmic cradles, regions where galaxies were forming and supermassive black holes were beginning to take shape. The recent discovery about how black holes feed themselves is a direct result of these capabilities. By analyzing the light emitted by accretion disks and the surrounding interstellar medium, Webb has provided unprecedented detail about the processes that fuel these cosmic engines. For instance, observations suggest that black holes may regulate their own growth by expelling excess material through powerful winds or jets, a mechanism that could explain why their growth rates align with the evolution of their host galaxies. But to fully appreciate the significance of Webb's findings, it's essential to understand the context of earlier missions. The Hubble Space Telescope, for example, was instrumental in mapping the distribution of supermassive black holes and studying their environments. Its observations of galaxy clusters revealed how black holes can influence the surrounding gas, preventing it from cooling and forming stars. Similarly, the Chandra X-ray Observatory's studies of accretion disks provided crucial insights into the temperatures and densities of the material spiraling into black holes. These findings laid the groundwork for Webb's more detailed investigations, which now extend to the earliest stages of black hole formation. By combining data from Hubble, Chandra, and other observatories, scientists have built a comprehensive framework for understanding how black holes interact with their surroundings, a framework that Webb's discoveries are now refining. The evolution of our understanding of black holes is a testament to the power of scientific curiosity and technological innovation. From Einstein's equations to the first images of black holes, each breakthrough has built upon the last, revealing new layers of complexity. The James Webb Space Telescope's recent findings about how black holes feed themselves are the latest chapter in this story, a story that continues to unfold as astronomers push the boundaries of what is possible. As we look to the future, the lessons learned from decades of observation will undoubtedly guide the next generation of discoveries, ensuring that the mystery of black holes remains one of the most captivating and dynamic areas of astrophysics. The James Webb Space Telescope has revolutionized our understanding of how black holes feed themselves, revealing intricate details about the accretion disks that swirl around these cosmic giants. Yet, even with its unparalleled resolution and sensitivity, the telescope has uncovered more questions than answers. Scientists are now grappling with a series of unresolved mysteries that challenge our current models of black hole behavior. One of the most pressing questions revolves around the exact mechanisms by which supermassive black holes accumulate mass. While we know that these colossal entities draw in gas, dust, and even stars from their surroundings, the precise pathways through which this material spirals inward remain unclear. The JWST has provided stunning images of accretion disks, but these disks are shrouded in complexity. For instance, the temperature gradients within these disks, where the inner regions are scorching hot and the outer layers are cooler, may not be as uniform as previously thought. Some researchers suspect that turbulence or magnetic fields could play a more significant role in shaping these disks than previously assumed. This turbulence might create pockets of denser material that accelerate the feeding process, but how these pockets form and how they interact with the black hole's gravity is still a topic of debate. Another enigma lies in the role of magnetic fields in black hole accretion. The JWST's observations have hinted at the presence of magnetic fields around these cosmic monsters, but the exact configuration and strength of these fields remain uncertain. Magnetic fields could influence how material is funneled into the black hole's event horizon, potentially creating jets of high-energy particles that shoot out from the poles. However, the extent to which these fields are involved in the accretion process is not yet fully understood. Some scientists argue that magnetic fields might even act as a braking mechanism, slowing down the inflow of material and altering the dynamics of the accretion disk. These competing theories highlight the complexity of black hole feeding and the need for further investigation. The interplay between black holes and their host galaxies also presents a puzzle. While we know that supermassive black holes are often found at the centers of galaxies, the relationship between their growth and the evolution of their host galaxies is still under scrutiny. The JWST has provided evidence that the growth of a black hole can influence the star formation rates in its galaxy, but the exact mechanisms of this feedback loop are not yet clear. For example, the energy released by a feeding black hole could heat the surrounding gas, preventing it from collapsing into new stars. However, the timescales over which this feedback occurs and the efficiency of this process vary across different galaxies. Some studies suggest that the interaction between the black hole and its environment might be more nuanced, with multiple factors such as the presence of dark matter or the density of the interstellar medium playing a role. These complexities mean that the relationship between black hole growth and galaxy evolution is still a work in progress. The role of mergers in feeding black holes is another area of active debate. When two galaxies collide, their central black holes can merge, releasing an enormous amount of energy in the process. The JWST has observed such mergers, but the frequency and impact of these events on black hole growth remain uncertain. Some researchers argue that mergers are a significant source of mass for supermassive black holes, while others suggest that they are more of a secondary factor compared to the steady accretion of gas and dust. The challenge lies in quantifying the contribution of mergers to black hole growth, as these events are rare and difficult to observe in detail. Additionally, the JWST's observations have raised questions about the diversity of black hole feeding mechanisms. While most studies focus on the accretion of gas and dust, there is growing evidence that black holes might also consume other materials, such as stars or dark matter. The recent discovery of tidal disruption events, where a star is torn apart by a black hole's gravity, has added new dimensions to this discussion. However, the frequency of such events and their significance in the overall feeding process are still debated. Some scientists speculate that tidal disruption events could be more common than previously thought, while others argue that they are relatively rare and may not contribute significantly to the long-term growth of black holes. These uncertainties underscore the need for more data and refined models to fully understand the range of ways in which black holes sustain themselves. Observational challenges also play a role in the unresolved questions surrounding black hole feeding. Despite the JWST's advanced capabilities, there are limits to what it can detect. For example, the extreme conditions near a black hole's event horizon make it difficult to observe the exact moment when material crosses the point of no return. Additionally, the presence of dust and gas in the accretion disk can obscure certain features, making it challenging to distinguish between different models of black hole behavior. These observational limitations mean that some aspects of black hole feeding may remain beyond our current reach, at least for now. Finally, the broader implications of these mysteries extend beyond black hole physics. Understanding how black holes feed themselves is crucial for unraveling the mysteries of galaxy formation, the distribution of dark matter, and the large-scale structure of the universe. For instance, the energy released by feeding black holes could influence the formation of cosmic structures, but the exact mechanisms of this influence are still unclear. Moreover, the study of black hole feeding provides insights into the fundamental forces of nature, including gravity and electromagnetism. As scientists continue to refine their models and gather more data, these unresolved questions will undoubtedly drive new discoveries and deepen our understanding of the cosmos. The journey to uncover the secrets of black hole feeding is far from over, and each new finding brings us closer to answering the questions that have puzzled astronomers for decades. As we look ahead, the scientific community is already planning a series of missions and instruments that could build on these groundbreaking discoveries. The James Webb Space Telescope has already provided unprecedented insights into the feeding mechanisms of black holes, but its work is far from over. In fact, the data it has collected is just the beginning of a much larger story. Future missions and advanced observational techniques will allow us to probe deeper into the mysteries of black hole accretion, test the limits of our current theories, and potentially uncover entirely new phenomena. These efforts are driven by a combination of technological innovation, international collaboration, and the ever-growing curiosity to understand the universe's most enigmatic objects. Let's explore what's coming next and how these upcoming projects could shape our understanding of how black holes sustain themselves. One of the most anticipated follow-up missions is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. While its primary focus is on dark energy and exoplanet research, its wide-field camera and infrared capabilities will also enable astronomers to study the environments around black holes with remarkable precision. By observing the light emitted from accretion disks and the surrounding interstellar medium, the Roman telescope could help refine our models of how material spirals into these cosmic giants. Its ability to capture large swaths of the sky will also allow scientists to track changes in black hole activity over time, potentially revealing patterns that were previously hidden. This mission could act as a bridge between the JWST's findings and the next generation of space observatories, offering a more comprehensive view of black hole behavior. Another key player in the future of black hole research is the Euclid Space Telescope, developed by the European Space Agency. Scheduled for launch in the early 2030s, Euclid will focus on mapping the distribution of dark matter and dark energy across the universe. While its primary goal is to unravel the cosmos' accelerating expansion, its observations could indirectly shed light on black hole dynamics. By studying the large-scale structure of the universe, Euclid may help scientists understand how supermassive black holes influence the formation and evolution of galaxies. This connection is crucial because the growth of black holes and the development of their host galaxies are thought to be deeply intertwined. If Euclid's data reveals unexpected correlations between black hole activity and cosmic structures, it could challenge existing theories or provide new clues about the role these objects play in shaping the universe. Beyond space-based observatories, ground-based telescopes are also set to play a critical role in advancing our understanding of black hole feeding mechanisms. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical telescope ever built. With its massive 39-meter mirror, the ELT will have the resolving power to peer into the hearts of distant galaxies and capture detailed images of black hole accretion disks. This will allow astronomers to study the physical processes occurring in these extreme environments, such as the temperature, density, and magnetic fields of the material surrounding the black hole. The ELT's ability to observe in the near-infrared spectrum will also complement the JWST's findings, providing a more complete picture of how black holes interact with their surroundings. Additionally, the ELT's spectroscopic capabilities could help measure the velocities of gas clouds near black holes, offering insights into the forces at play during accretion. In the realm of high-energy astronomy, the upcoming LINX X-ray Observatory, proposed by NASA, represents a major leap forward. Scheduled for launch in the 2030s, LINX will be equipped with an advanced X-ray telescope capable of detecting the intense radiation emitted by black holes as they consume matter. X-rays are particularly useful for studying black hole activity because they can penetrate the dense clouds of gas and dust that often surround these objects. By analyzing the X-ray emissions from accretion disks and relativistic jets, LINX could reveal details about the extreme conditions near the event horizon of a black hole. This data will not only help confirm existing models of black hole feeding but may also uncover new phenomena, such as previously undetected interactions between black holes and their environments. Meanwhile, the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory, is set to revolutionize our understanding of black holes in a completely different way. Unlike traditional telescopes, LISA will detect ripples in spacetime caused by the mergers of massive objects, including supermassive black holes. These gravitational waves will provide direct evidence of how black holes grow through collisions and mergers, offering a new perspective on their feeding mechanisms. By observing the mergers of binary black hole systems, LISA could reveal how these events contribute to the overall growth of supermassive black holes. This information will be invaluable for testing theories about the role of mergers in black hole evolution and could even challenge existing models if the observed data doesn't align with predictions. The synergy between these missions will be crucial in piecing together the full story of how black holes sustain themselves. For example, while the JWST provides a detailed view of the infrared light emitted by accretion disks, the LINX X-ray Observatory will capture the high-energy emissions that occur in the same regions. Combining these datasets could allow scientists to model the entire spectrum of radiation emitted by black holes, offering a more comprehensive understanding of their feeding processes. Similarly, the ELT's ground-based observations will complement the Roman telescope's widefield surveys, enabling a more detailed analysis of how black hole activity varies across different cosmic environments. However, these future missions are not without challenges. One of the primary obstacles is the sheer scale of the data they will generate. The Roman telescope, for instance, will collect vast amounts of information from the universe's most distant regions, requiring advanced computational tools to process and analyze it. Similarly, LISA's gravitational wave detections will need sophisticated algorithms to filter out noise and identify genuine signals. These challenges highlight the importance of interdisciplinary collaboration, as astronomers, computer scientists, and engineers will need to work together to make the most of these groundbreaking instruments. Another exciting frontier is the potential for multi-messenger astronomy, which combines observations from different types of signals such as electromagnetic waves, gravitational waves, and neutrinos to study cosmic phenomena. The Event Horizon Telescope, EHT, which recently captured the first image of a black hole's shadow, has already demonstrated the power of this approach. Future collaborations between the EHT, the JWST, and missions like LINX and LISA could provide a more holistic view of black hole feeding. For example, if a black hole's accretion disk is observed in both infrared and X-ray wavelengths, scientists can cross-reference these data to infer the physical conditions in the disk. Similarly, gravitational wave detections from black hole mergers could be linked to electromagnetic observations of the surrounding environment, offering insights into how these events influence the broader cosmic landscape. As these missions progress, they may also challenge existing theories about black hole behavior. For instance, if the Roman telescope detects unexpected variations in the light emitted by accretion disks, it could suggest that our current models of black hole feeding are incomplete. Similarly, if LISA observes mergers that don't align with predictions about how supermassive black holes grow, it could force scientists to revise their understanding of these processes. These potential surprises underscore the dynamic nature of astrophysical research, where new data often leads to new questions and, ultimately, new discoveries. In addition to confirming and extending our current knowledge, these future missions may also open up entirely new avenues of inquiry. For example, the study of black hole feeding could lead to a better understanding of dark matter and dark energy, as these phenomena are believed to be interconnected with the large-scale structure of the universe. The Euclid telescope's focus on dark matter could provide clues about how black holes influence the distribution of matter in galaxies, while the Lynx Observatory's high-energy observations might reveal new interactions between black holes and dark matter particles. These connections highlight the far-reaching implications of black hole research, showing how studying these cosmic giants can shed light on some of the universe's greatest mysteries. Ultimately, the journey to understand how black holes feed themselves is just beginning. The James Webb Space Telescope has already provided a remarkable glimpse into this process, but the data it has collected is just the starting point. Future missions like the Roman telescope, Euclid, the ELT, Lynx, and LISA will build on these findings, offering new tools and perspectives to explore the complexities of black hole accretion. As we look to the future, the collaboration between these cutting-edge observatories will not only deepen our understanding of black holes but also push the boundaries of what we know about the universe itself. The next chapter in this story is being written right now, and it promises to be as thrilling as the discoveries that have come before it. James Webb Space Telescope discovers how black holes feed themselves. This part of our deep dive into James Webb Space Telescope discovers how black holes feed themselves focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.